Alright, so let's pick up the story here at partial derivatives of differentiable maps. So, I should mention, I'm mostly focused on the finite dimensional case here. There is some concept which extends to infinite dimensions called the Gateau derivative. But you gotta be careful, this is defined different ways in different places. Anyway, I will leave that to your future studies. We'll focus on the finite dimensional case here. And the definition of a partial, well, we're not quite to the definition of partial derivative just yet. First, we want to define a directional derivative. A directional derivative is defined to be limit as h goes to 0, f of a plus hv minus f of a divided by h. Now, maybe I should make this h a t, so you're not tempted to think of h being a vector. I mean, in the Frechet quotient, h was a vector. Here, this is h is a real number. And so what we're really looking at is we're looking at data. We're looking at the function evaluated on a line, if you will, a line through A with the line has base point A, it has direction vector v, and has parameter t. So I mean, really, I regret this. I mean, I really should have a t. I mean, I think it'd be better to put t here and tv and divide by t. That would be better because, that way you wouldn't be tempted to confuse this with the limit as h goes to 0, where h was a vector. All right. So this is the directional derivative of f at a in the direction v. Now, if we set v and w both to be the reals, this just goes back to the ordinary derivative. Now, Isaac, I'm in the middle of something, buddy. I can't talk to you right now.
No one's helping me do school.
I told Daniel to help you.
He's not helping.
Well, tell him to help you, otherwise there'll be consequences. Thank you. Again, my apologies for the distractions. So busy partying here. It's hard to focus on school somehow. Alright, now, I'm going to need my piece of paper. Sorry guys, I'm looking for my cover sheet. So, first of all, I mean, there's another significant difference between the directional derivative here and the one you saw in Calculus 3 is that here we do not assume that v has unit length. V could be a vector of arbitrary length. Let v and w be normal linear spaces. If you had a function which is differentiable at a point, then guess what? The directional derivative at that point exists, and here's the connection. D sub big sub dv f of a is the differential at a acting on v. Simple as that. Now the proof of this looks more complicated than it is, so let me go through it. First of all, if the function is differentiable, we have that this limit exists. This is a vector limit, right? But you can set h equal to, you can set that h equal to tv for any, any path approaching the origin. So thinking of h equal to tv in some sense, if we look at t goes to tv, then this can be passed through the origin. And so for t greater than 0, the reason that we look at t greater than 0 is so that I can rewrite this as limit as t goes to 0. I can pull out the norm of v, absolute value of t. Of course, absolute value of t is just t again, if t is positive, and we get that, right? Now, but on the other hand, we also know that this difference is equal to that. I mean, that follows from this. This goes to that, right? This limit exists because the differential exists. Consequently, this difference quotient has a limit which exists. This is much like the first example we did, connecting the Frechet derivative with the ordinary derivative right after we introduced the definition of Frechet differentiation. And likewise, for the path t goes to tv for t less than 0, so like geometrically what's going on here is, here's 0, right? There's this path, and then there's that path. So maybe this is t greater than 0, maybe this is t less than 0. If I draw that, I'm thinking of, the vector v being something like that, But of course you can do that for arbitrary v going through the origin, and that gives you information. Let's see here. So getting back to my argument here. So for the negative time path, we get this. This time absolute value of t is actually minus t. And so that gives us the left limit is this. We have the right limit is that. So the double-sided limit is that. And consequently, that's the directional derivative. df of a plus t of v minus f of a divided by t is equal to df a. Notice I've now adopted the notation t instead of h by the time of this proof. Unfortunately, I forgot to go back and edit the definition. So sorry. Anyway, d sub v f of a is equal to the differential of f a of v for all v equals 0, since of course you can get the v equals 0 case trivially, right? I mean, if v equals 0, it's just f of a minus f of a. That limit is just 0. So cool. Okay, so that's the connection between the differential and the directional derivative. That brings us to define very particular directional derivatives, so-called partial derivatives. With respect to a basis, beta in a normed linear space, we define the directional derivatives in the direction of the basis to be partial derivatives with respect to the coordinate functions. This same definition is given in Calculus 3 in the context of functions from Rn to R, or if your instructor was adventurous, maybe Rn to Rm. Probably not. And it's nice to rewrite this limit as a derivative, right? This ties into our previous discussion with derivatives of vector-valued functions of a real variable. There it is. And so then we can calculate partial derivatives of functions on a normed linear space, provided we got a basis, you know. I mean, partial differentiation is naturally attached to a basis. The Fréchet derivative, in great contrast to linear transformation, it has no particular concept of basis, and that's one of its advantages, is coordinate-free construction. We went through this in class already, so move along here. I also mentioned to you in class that we can build differentials from partial derivatives. If we have a function which is differentiable at a, then you can calculate its differential in terms of the partial derivatives, like so. The calculation is simple linear algebra. So we have dfa of h of vi. Pull out the h by linearity of the differential. Then I pull out the, I then use the previous theorem, which said that the differential of f at a acting at vi was the directional derivative in the ith direction of f at a. And then by definition, that's the partial derivative of f with respect to xi. And there you go. That's it for arbitrary. This is for arbitrary h, and so that's that formula right there. And then I used that last class also to reconstruct the differential of the square map from partial derivatives, like so. I'm not sure, I haven't checked this myself, but there's a problem I assigned you in Mission 2 that involves calculating the differential of the exponential function. I seem to have some memory that was difficult to do directly in terms of the definition. This might be a good thing to try out for that. Maybe you can calculate the partial derivatives of the exponential map and then use this procedure to construct the differential. That might be productive. I don't know. What's so exciting, Benjamin? I'm holding Benjamin here. He's keeping us company. Okay, so at this point, I behave. I stop talking about normed linear spaces for the most part. I just start talking about functions from Rn to Rm. Or in this case, from Rn to Rn. That's supposed to be, my apologies, this guy right here is supposed to be an M. Okay? Then this guy is supposed to be an M. Oopsie. Oh, no. The domain M. So that's supposed to be an N in mid-range. Wait a minute. I'm an idiot. Let's try that again. So it's from Rn to Rm. If we do that, the matrix of a linear transformation will be M by N. That's why I put the M in the range, and the N is in the domain. It's just to get an M by N matrix, if you want to know the reason for the positioning of the letters. It's just that. It's just sort of customary. So if we have a linear transformation from Rn to Rn, the standard matrix is we take the linear transformation acting on E1 for the first column, E2 for the second column, En for the nth column. When we apply that idea to the differential of linear transformation, we have df a of E1 and so forth and so on. But of course these are partial derivatives. with respect to the first, second, and nth variable. So the matrix of the differential, as I mentioned to you guys before, is called the Jacobian matrix, and it's related to the partial derivatives column by column. Before I get to that, let me just pause here for a second. If you didn't remember geometric meaning of partial derivatives for like a function two variables, you know, it has to do with like the slope of the function if we look at the trace of the graph restricted to, you know, like fix one of the variables and let the other one vary. Partial derivative tells us the slope. So you guys know the story. The partial derivative describes the change in a function while we fix one thing and one thing vary and fix everything else. That's what it's about. So at the next page or two, I just have some really nice just formulas for what the Jacobian matrix looks like in terms of partial derivatives. Here's the gory full story. The first component function fills up the first row. Second component function, second row. Mth component function, mth row. First derivatives with respect to x1, derivative with respect to x2, derivative with respect to xn. So getting to the point here, there's really two ways to look at the Jacobian matrix. We can either look at it as a bunch of partial derivatives of the function with respect to the first, second, all the way up to the nth variable, just glued together like that, column by column. I find that that's a pretty useful way to actually calculate it, and I got tons of examples here coming up. Benjamin will let me look at it. Want to say hi? Say hi to the people. Hello. All right. But let's see here. On the other hand, you can look at it as a stack of gradient vectors, right? Gradient of the first component function and so forth. Now, my first example here is actually to recreate the example I started with today and show that you can build the differential of this function using partial differentiation. So the partial derivative of this guy, right? So the way we should really think about f is like this. It's xy, x squared, and x plus 3y, like so. So if I take the partial derivative with respect to x, I get that, right? If I take the partial derivative with respect to y, I get that, right? Because this has no y dependence, whereas that has the 3, this gives me an x, and so forth. So there's the differential at xy built from partial derivatives, which is what we found before using a direct and cumbersome limiting argument. And then over here, oh, well, there's actually what I just wrote out. Sorry. Okay, so next up, I have tons of examples coming up, but just one more sort of formula. In retrospect, we can also build the differential, I mean not the differential, but the directional derivative from partial derivatives like so, right? The directional derivative of f at a in the v direction is built from partial derivatives like so. In fact, a lot of textbooks will use this as the definition of directional derivative, but I would say that that's sad. The proof of that's pretty simple. Here it is. Okay, so again, standard directional derivatives down here. It's the dot product of the gradient vector with the velocity. And in Calculus 3, we insist that the length of v be 1, but we make no such assumption here because we're interested in studying the theory of differentiation, not just using directional derivative to solve like certain applied problems. So next up, I have a laundry list of examples of Jacobian matrices, and I won't say much about those. I would encourage you to look over them. Lots of nice examples here. You know, always notice like this one. Stop and smell the roses here. This goes from from R3 to R3, so it's a square Jacobian matrix. This one goes from R3 to R2, so that means it's got a two rows by 3 column Jacobian matrix. This one goes from R2 to R3, so it's got a 3 by 2 Jacobian matrix. So you can kind of make sure. I think that you probably can work through, you know, a third of these and still get the idea. I don't know why I've got so many examples here. I just anyway. So here they are. Examples after examples after examples of Jacobian matrices out the wazoo. I think this one's kind of neat. So here we have the function as the cross product with a fixed vector, and calculate the Jacobian matrix to be that. So this multiplication by this matrix is the same as taking the cross product with V. That's kind of neat. But anyway, tons of examples. So the other thing we should sort of connect back with is the idea that the chain rule, we derived the chain rule for normed linear maps, but now we can connect with the Jacobian matrix, and we can see some of these chain rules that you were taught in Calculus 3 coming from matrix multiplication, like this one, for example. If we have a function from R2 to R, f, and then we have another function, if we have x and y as functions of u, v, and w, then we can compose, right? We can compose f and r to get a function from R3 to R. Now, the Jacobian matrix of f would be partial f, partial x, it's a row vector. The Jacobian matrix of R would be this 2 by 3 matrix, right? xu, xv, xw, yu, yv, yw in the usual shortcut Calc 3 notation. And so when we look at the Jacobian of the composite, the chain rule, so the chain rule says, the one I proved was that if we look at the differential of f composed with r at a, right? It was the differential of f at r of a composed with the differential of r, right, at a. Although I suppose a here would be u comma v, but I'll just use a as a sort of generic label there. And then the thing we learned in linear algebra is the matrix of a linear transformation, if it's composite, then the matrix of the composite two linear transformations is what? It's the product of the matrices being composed, the standard matrices, like so. Sorry, I've lost a lot around the room there. Now, of course, that just looks like f composed with r prime is f prime r prime in the notation being used here. But understand that that's just using that chain rule that I almost proved earlier today, and the notation f prime r prime for the Jacobian matrix. But then you see multiplying these gives you these three component functions, which you may recall as being the partial derivatives partial chain rules we taught you in Calculus 3 for such a composite function. So I think that's kind of neat. We can derive all of the chain rules we learn of in Calculus 3 by multiplication of Jacobian matrices. Here's another one. If I have the composite of a path, f is a path, it's from R to Rn, and a function, a real valued function of Rn, g, well, the Jacobian matrix of the path is this in this case it's this column vector of velocities, and the Jacobian matrix of the function is a gradient vector. It's a row vector of partial derivatives. And when you multiply these Jacobian matrices, out pops the usual chain rule for the composite of a path and a level function, which is, of course, so important to Calculus 3. All of these things being derived from that one overarching argument we gave earlier today, right? Is that all the same chain rule for normed linear spaces reproduces all of these chain rules. I've got a homework problem that's kind of like this for you guys, so if you might, well, it's not, it's sort of like this, so, well, I don't know, there's a homework problem that's kind of the same spirit of this, but it's not quite the same. You can tell Calculus 3 next semester about this example. This is the derivation of the Laplacian in polar coordinates in all of its awful glory. Let me go on here. So our next topic is how to go the other direction. I've showed you that if the function is differentiable, then we have directional derivatives, and when we specialize to coordinate direction, those are partial derivatives, they exist, right? But how about the other direction? What if you're given that directional derivatives exist, that partial derivatives exist? Can you then go back and say that the function is differentiable at the point? Is there a converse to this direction of inquiry we've been studying? And the answer is not always. And to make clear this concept, we have to discuss what's called continuous differentiability. So that's what's up next. I'm going to stop it here and pick it up again in a minute.